Good afternoon to everyone. I'm Giulio from BIPM, and today we present you the use of GNSS and especially IGS product in the computation of UTC. So a bit of motivation for the presentation. As you probably know, UTC is the international time standard, so it's the time scale that tries to unify on the national time scale. And to compute UTC, the GNSS techniques are fundamental, and in particular, when computing UTC, we make extensive use of IGS product. And so, we will see how the better IGS product means also that we can make a better UTC. And so, first of all, let me thank you, the IGS community, to provide such great product. Without them, UTC will not be possible to the current accuracy. So, maybe not every one of you know what is UTC. So, UTC is a post-process time scale that is computed at the BIPM, which is the French acronym of the International Bureau of Weight and Measure, that is the international organization that oversees many fields of world metrology. And since the 1988, each month we publish the so-called circular T, where all the difference between UTC and all so-called UTCK, so each different lab is tabulated each 5 days. You can see here the first circular T and the last one. In this graph, you can see the evolution of the UTC minus of UTCK for some selected lab since the late 90s to today, and you can see we have moved to a difference of about dozens of nanosecond to few nanoseconds. Actually, you cannot see here, but the best labs are synchronized to better than a nanosecond nowadays. So what is the role of GNSS in the computation of UTC? To compute the time scale, we need to compare clocks in different labs. So for instance, in this slide you can see a sketch with some clocks in one lab and some clocks in the other lab. And these clocks are used internally by the labs to generate the local time scale, and the local time scale is fed to a timing receiver which use the timing information of the time scale. And then we can, thanks to the GNSS receiver, we can compute the difference between the local UTCK and a GNSS time scale, for instance GPS time, linear time, or IGS time. And then by difference, once we do this at two labs, we can compute the difference between the two time scale, UTCK1, UTCK2. So this is the map of the labs that participate in UTC. So in yellow you can see all the labs which maintains an UTCK, and in red you can see the UTCK labs which also contribute to IGS. And this means through these labs it is possible to access the very stable UTCKs of many labs. You can see two of them in North America, many in Europe, and one in Asia and South America. And also this means that since these labs are temperature controlled, the bias of this station will be very stable, and I will show later we also calibrate this station, so you can also have the bias for this station. So a brief schematic to show where the IGS products are used in UTC. So two types of time links are computed operational for the UTC computation. The first one is PPP links. We are computed using the combined IGS rapid ephemeris, and we also use IGS rapid ephemeris and tech map to correct for lower precision Pseudorange based link which are used as a backup. So the current PPP solution is a a PPP solution of 35 days, which is computed with the GPS PPP software from NRCAN, which is an open source software, and is GPS only and is a Kalman filter forward and backward with float ambiguities. For instance, in this slide you can see the difference between UTC US North, one of the most stable UTC, and the IGS time rapid time scale. To connect the clocks, one step is missing, so the calibration of the hardware delay. In the timing community, normally we sum together the antenna and the receiver delay to a quantity called in delay. We measure the antenna cable delay with the time interval counter, which is very easy, and also we can measure the difference between the timescale reference point and the receiver reference point. So the cable and reference delay can be measured with a time interval counter. For the antenna receiver delay, we need to have a calibration procedure. And so the IPM circulate a box containing 2 timing receiver and 2 antennas to some labs called G1 labs, which are the most important some labs that volunteer in the regional meteorological organization, which are EURAMET for Europe, SIM for North South America, APMP for Asia Pacific, and COMET from Eurasia. And the IPM circulated this box to calibrate the delays of this station. And then subsequently, each lab in the regional meteorological organization calibrates the other lab. And for timing, we calibrate currently 3 constellations, GPS, Galileo, and BDS3, and we calibrate L1 and 2 for GPS, E1 and E5A for Galileo, and B1C, B2A for Beidou 3. In the graph, you can see the repeatability of this calibration. Here, GPS is shown because it's the one that is calibrated since a longer time. So the calibration are done each 2 years, and you can see here are the receiver maintained in the G1 labs, and you can see the repeatability of the calibration is around 400 picosecond. And of course the mean has been removed in this graph. And this, all these calibration values are public and are accessible to a web database on the BIPM website, and we also collect absolute calibration performed by some UTC labs on the receiver. So we currently use this only for timing, but I may assume this could be helpful also for other geodetic activities, so the data are free. If you want to use them, we are happy to exchange with you. So the evolution of the PPP solution for UTC, past work of BIPM colleagues together with the colleagues from the French Space Agency CNES showed that fixing the ambiguity really has a great impact on the time transfer solution. And these pioneer works were done using GPS only, but nowadays we know that integer products are available for the 3 global constellations. And also this is very important because nowadays the most accurate frequency standards are so precise that actually the time transfer technique is the limiting factor for the stability and frequency accuracy of UTC. And so if we could have an operational multi-constellation PPP solution with ambiguity fixing, we could really improve the quality of UTC. When we try to do a multi-day time transfer solution, one of the biggest challenges are the discontinuity at the day boundaries. And for this, I thank the one colleague for introducing this problem before me. So there are some jumps in the time scale which are in principle not a big problem because they will be eliminated in the baseline difference. Also some, maybe we can have some jump in the inter-system bias for which we can set up an unknown. But more challenging are narrow lane steps on the satellite. So if we refer the clock to the INO3 phase combination, we can see that from one day to another there can be some narrow lane integer steps, and these, if there are too many of them, the continuity of the solution is broken, and so the timing solution really is impacted by this. And for this we, thanks on any work by the IGS to reduce this discontinuity. We have seen the presentation from one, and the BIPM really appreciate this work. And to remove this narrow lane jump, if the clock are stable enough, typically hydrogen maser or the new Rubidium space atomic clocks, we can try to use the stability of the clock to estimate this narrow lane jump and to remove it. And this can be done either on the ground station or with a bit less performance on the satellite side. At the BIPM we compute in post-processing an IPPP solution using G software for GNSS, and we decide together with a colleague from the Royal Observatory of Belgium and the National Research Council of Canada to do a comparison of IPP software, and we have presented this work last week at a conference in Neuchâtel. And well, first of all, we started to compare the PPP solution with fiber optics data, which Polish colleagues maintains between two laboratories in Poland, and we can see that the average frequency difference is around a few parts 10 to the minus 18. So we decide to compare a longer baseline, so we selected two stations in Europe, two stations in Asia Pacific, and two stations in North America, and we compute the difference between all the software. And in the heat map you can see the difference ordered by baseline length, and you can see we move from few parts to 10 to the minus 18 to some part to 12 minus 17, and we are currently trying to figure out what is the reason for this. So if anyone from the IGS would like to work on time transfer, we really would appreciate all the expertise from the IGS. So this brings me to the conclusion. We make extensive use of IGS product for UTC. We would like to go from a flow to fixed solution, also multi-constellation, and continuity in the IGS product will make this effort much easier, and also we maintain some hardware delay calibration that maybe could be beneficial for the work community. Thank you very much.